Alright, welcome back. Today we'll be doing number 1 from section 6.1 in the textbook, and in this problem we are given a 2x2 matrix A, and we are tasked with finding eigenvalues with each respective power. Afterwards, we will also be looking at a couple conceptual questions related to the eigenvalues. To start, we learned that from section 6.1 that there is an eigenvector x that lies along the same line ax, such that ax will be equal to lambda x, where lambda is the eigenvalue. We also know that when ax equals lambda x, that the determinant of a minus lambda I will equal to 0, meaning that the matrix a minus lambda I will be singular. So what is a minus lambda I in this case? So given a to be 0.8, 0.3, 0.2, and 0.7, a minus lambda I will be 0.8 minus lambda, 0.3, 0.2, and 0.7 minus lambda. And this has to be equal to 0. So a determinant for a 2x2 matrix is going to be AD minus BC. So AD in this case will be 0.8 minus lambda times 0.7 minus lambda minus the product of 0.3 and 0.2. If you simplify this becomes 0.56 minus 1.5 lambda plus lambda squared minus 0.06. And further, lambda squared minus 1.5 lambda plus 0.5 will be equal to 0. To find the lambda values, we just have to factor this. And if you got the correct combination, it should be lambda minus 1 and lambda minus 0.5. So for A, lambda equals 1 and 0.5. For the other powers, a squared and a infinite, we look back to the expression ax equals lambda x, and we observe that a and lambda are directly proportional. So all we have to do to one side, we do the other. So for a squared, we squared a, so lambda also has to be squared. Thus, 1 squared equals 1, and 0.5 squared equals 0.25. Thus, 1 and 0.25 will equal lambda for a squared. Same thing for a infinite. We just have to raise lambda to the infinite power. So 1 to the infinite power will be 1, and 0.5 to the infinite power. So higher powers for 0.5, it will get significantly smaller over each exponent. So 0.5 to the infinite power will be trending towards 0. Thus, 1 and 0 are the eigenvalues for a infinite. Okay, and that concludes part 0. For part A, we turn back to A. So we have A to be 0.8, 0.3, 0.2, and 0.7. And we have to show that how row exchange for A can produce different eigenvalues. So we row exchange A, and then we call it B. So then we would get 0.2, 0.7, 0.8, and 0.3 when we row exchange A. So from here, let's just find the eigenvalues then. So again, determinant of B times lambda I has to be 0. But what is this? This is just going to be 0.2 minus lambda, 0.7, 0.8, 0.3 minus lambda. This has to be 0. Alright, from here, AD minus BC will give us 0.2 minus lambda times 0.3 minus lambda, subtracted by the product of 0.7 and 0.8. If you simplify this becomes 0.06 minus 0.5 lambda plus lambda squared minus the product, which is going to be 0.56. And this simplifies to lambda squared minus 0.5 lambda minus 0.5. To factor this, the correct combination would be lambda minus 1 and lambda plus 0.5. Thus, lambda for b, the eigenvalues for b will be 1 and negative 0.5. And we have to show that they're different, and we can see that they're different because eigenvalues for b is 1 and negative 0.5, and the eigenvalues for a is 1 and 0.5. And this proves that a row exchange does produce different eigenvalues. Alright, lastly, let's move on to b. And for b, we have to explain why a zero eigenvalue is not changed by elimination. So again, from section 6.1, we learned that singular matrices will always have 0 as an eigenvalue. Also, as you may have noticed from past problems and concepts, that elimination also shows that a singular matrix or singular matrices will also stay singular. Elimination does not change the property of singularity. And from these two statements, we can conclude that, yes, hence, lambda equals to 0 will not change by elimination. Because if elimination does not affect singularity, it will not affect the 0 eigenvalue. Which this should be sufficient reasoning for part B, which would conclude this problem. So thank you guys for doing this with me again, and I will see you guys next time.